Hello, my name is Brandon Thiessen. This is my mid-semester walkthrough of the My Shell project for CSC209 Winter 2025. First, we are going to compile the code. As you can see, the code compiles successfully without any errors. Next, I'm going to demonstrate the definition and redefinition of variables in the shell. We initialize a new variable a and set its value to 1. We then use the echo command to display the string with only the variable $a. Then, we reassign a to the string 2. Using the echo command again, we display the newly reassigned value of a. We can reassign the value of a as many times as we like. Consider another example of expansion when the input is truncated. We create a new variable long with 120 characters. Then this variable expansion is over 128 characters, so it will need to be truncated. This expansion is 4 characters for echo plus 1 character for the space in between echo and the first long, plus 120 for long, plus 1 character for the space in between the first and second long, which is already 126 characters. Therefore, to reach 128 characters, only 2 characters from the second long are kept in the input. As you can see, only 2 characters from the second long are kept in the variable expansion. Next, I'm going to demonstrate a variable being expanded within the definition of another variable. Before any command or operation, such as the assignment operation, is applied to the input string, every variable expansion using the $sign operator is applied to the input string. In other words, every variable is expanded before anything else happens. This allows us to assign the result of the variable expansion $a to the assignment to variable b. We can do other interesting things with this. We assign the string echo to the variable c, and then when we expand the variable c followed by some string, the fully expanded input string looks like, which displays. Next, I'm going to walk through the code that supports the storage of an arbitrary amount of variables. We use a linked list data structure to store the shell variables. In the variable's header file variables.h, there is a node struct, which is a node in the linked list. Each node represents an assigned shell variable. Each node has 3 fields: a char pointer name, which stores the name of the variable, a char pointer value, which stores the string value of the variable, and a node pointer, which points to the next node in the linked list. Every variable-related function is stored in the variables.c file. This global vlist variable is the head of the linked list storing all of the shell variables. Beginning with the setVar function, setVar takes in a name string and a value string. We set our node pointer cur to vlist, the head of the shell variable linked list. Since we need to support variable reassignment, we begin by traversing the list to see if there are any variables with matching names. If we find a name that matches, we free the memory holding the value, and then update the value field. If we do not find a matching node in the list, we create a new node with the corresponding name and value, and insert the node at the head of the list. Next, we have the getVar function. GetVar takes in a string parameter name. GetVar returns a char pointer, which is the value of the variable, or null if no variable is found with the given name. Again, we set cur as vlist, the head of the shell variable linked list. We then traverse the linked list in a while loop, checking if there are any matching nodes with the given name. If we find that node, we simply return the corresponding value field of the node. If we have searched the entire list and have no matches, we return null. Finally, we have our freevars function. Freevars will traverse the vlist shell variables linked list, and for each node, we'll save the current node in a temporary variable and update cur to avoid dangling pointers. Free the name and value fields, and then free the node itself. Then, after every node is free, vlist is set to null, again, to avoid dangling pointers. Freevars is called when the shell exits, as the shell variable list is now no longer in use, and must be freed to avoid memory leaks. Using a linked list approach in storing shell variables is good because it allows for dynamic allocation of variables in memory, and can support an arbitrary number of variables. Additionally, this approach is simple to implement, and only requires a proportional amount of memory to store. However, this approach does come with some downsides. Most importantly, accessing variables could be worst-case O of n complexity. This can potentially be a problem when storing many variables, as variable lookup could become quite slow, potentially having to search the entire vlist shell variable linked list. Additionally, the node struct to store the variable attributes in is a bit of memory overhead, which could be avoided with other approaches. An alternate approach that I could have taken to implement the shell variable storage was to write the variables to a file. An advantage of this implementation is that it would allow for variables to exist across multiple shell instances. However, file I/O and parsing would be significantly slower than my in-memory solution, which could result in serious problems when using the shell. Next, I will walk through the code that handles the case when expansion leads to a string of over 128 characters. It may be useful to understand how the shell program parses inputs from the user. First, we get the input directly from the user. Then, we tokenize the input using the tokenizeInput function, which calls stir to k using spaces as a delimiter. After this, in this for loop, each token has the variable expansion applied to it, using expandVars. Here is the expandVars function. We then call truncate tokens on the token array, with the original token count given to us from tokenizeInput. Truncate tokens is implemented in iohelpers.c. Truncate tokens returns the updated number of tokens after truncating the combined length of each token to 128 characters. We set up an initial total length which we will add token lengths to later. Then we loop through each token in token array and get the length of the token with stir nlen. If the combined length of every token plus the length of the current token is greater than the maximum allowed length of the user input, we insert a null character exactly where 128 characters is reached, and then return the updated number of tokens. Otherwise, if this is not the case, we add the current token length to the total length, and then add 1 for the spaces in between the tokens. If we have iterated through every token, and the combined length of each token is not over 128 characters, we can simply return the original number of tokens, as no truncation is necessary. Recall our earlier example, where we set the variable long as a string 120 characters long. Consider the variable expansion echo long long. Looking at it through the lens of the truncate token function, we set I to 0 and look at the first token, echo. Echo is 4 characters long, so token len is set to 4. We add token len to total len and add 1 for the space between the next token. Incrementing I to 1, we look at the second token, long. Long is 120 characters long, so we set token len to 120 and add it to total len, and then add 1 for the space. We increment I again, and then set token len. However, when we add the token length to the total length, it is over 128 characters. Therefore, the 128th character of the entire input must be in this token. We calculate that max stir len, which is just 128, minus the current total len is equal to 2, and thus we set the 2-index character in the token to a null character. Therefore, when we run this command, we should see only 2 characters from the second long are kept in the input. A main benefit of this implementation is that it is simple, maintaining the integrity of most of the original input, and it is efficient, as it will stop immediately when the combined length is greater than the maximum length, making this function technically run in O of 1 time. However, it does come with a notable downside. It should be noted that the tokens that have been truncated still exist, and are still allocated in memory, meaning that there is still some unnecessary memory overhead. In mysh.c, we stored the original token amount before the truncation, so that when we are freeing the tokens, we don't stop early and cause a memory leak. An alternate approach that I considered was to reconstruct an input string using the expanded tokens in token array, stop constructing it if it reached 128 characters, and then use stir to k or tokenizeInput again to break the string into tokens again. The main reason I did not implement this solution was that it was too complex and convoluted. That concludes the code walkthrough. I appreciate your time. Thanks for watching.